my name is Nick, and today I'm going to talk to you about George Boole and Claude Shannon and what they did for math. Enjoy the show. Okay, to begin, I'd like to... Okay, there we go, that's better. So, today I'd like to begin with some historical background or just fun knowledge about who we'll be talking about. So to start, we have George Boole, who existed around in the 1800s, and he actually was self-taught because his family didn't come from the wealthiest background. He had to be extremely resourceful in finding books. He would work and volunteer at the libraries and schools, which was super cool. He self-taught himself many languages. He liked Greek, Latin. At the time, it really helped him bring the English mathematicians back up with those across the continent. He had a very unique family, as I mentioned. Comparatively, a lot of the educated people came from affluent families, whereas George didn't have the same privileges that others might have had. He was noted as a young genius in school. His teachers noticed he was moving quickly ahead of his classmates at a young age. And then to show this, at the age of 19, so around the age of us, he started his own school, organizing and running it, which is pretty impressive. And while I think I've got a little bit of my life together, I'm not sure I could do the same. And then I have a fun fact about George Boole, which is actually that he went on to marry Mary Everest. Everest, that last name sounds familiar. That's for a reason. It's because she was the niece of the man who discovered Mount Everest. So that is George Boole in just a quick nutshell for you. I hope that currently you think he is as wonderful as I do. Pretty cool guy. Now we'll move over to Claude Shannon. So over on the right we have Claude Shannon, who came around after George Boole's time in the 1900s, and he actually died in 2001, which is the same year I was born in. So unlike George Boole, he came from a wealthy socioeconomic background. His father was a judge, which did give him some benefits. At the age of 22, he published his master's on electrical circuitry, which is actually one of the reasons he got famous really quick. In this master's, he actually used the logic Boole kind of got started going, and he then applied it to electrical circuits as a way to almost test what would happen before practicing it. And then he pursued a PhD at MIT, and then went to work at Bell Laboratories. He also did a lot of work with communication, which during World War II was super helpful, and one of his biggest role models was Thomas Edison. Now for the fun fact about Claude, I'm gonna have to go get a prop.
"2,000 years later."
Anywho, for my fun fact about Claude, he actually in his home office had a certificate that called him a doctor of juggling. Claude is described as a very unique individual, fidgety, and he liked to do a very broad amount of things, and juggling was one of those things. Now for the fun stuff. So we're gonna get into what Boole's big boom or big research actually was. So it was kind of connecting math and English in a way. So he wanted a way to logically equate English sentences into mathematical logic. So for example, if you look at the statement x plus y, where x is all men and y are all women, based on English, you could say that all men and all women is equal to all women and all men. So in that sense, Boole introduced a logical way to prove why the addition of numbers works both ways. So for example, 2 plus 3 is 3 plus 2 because 5 equals 5. Woohoo! Pretty smart. And similarly, he proved the distributive property of multiplication through addition. So if we introduce a z, and we multiply z by a bracketed x plus y, because all of us are math people, we know it equals zx plus zy. But then if you think about tying in the English and logical component of it, why is that possible? So if we introduce z as defining the class of Europeans, we can know that all European men and women is equivalent to European men plus European women. So then if we look at it with numbers, if we equate z to 4, using the same 2 and 3 from above, we have 4 times 2 plus 3, so 4 times 5, which gives us 20. And then we have 4 times 2 plus 4 times 3, which gives us 8 plus 12, which again is 20. And so it's proven with numbers. Woohoo! I'd like to introduce some other things Boole presented. So he introduced 1 as being the universe and 0 as being nothing. In which case we have x and y, which would be the class of things that are both x and y. We have a class of x, which we can just say is x, because if all things that are x would define the class of all x's as well. So then we would have x and y, which would be a class of either x or y. We would have x minus y, which is all x's that are not y's. 1 minus x, which as we talked about up here, 1 being everything, minus x would be everything that is not x, which we could also say that x, 1 minus x was nothing, because all things that are not x and x are then nothing. Which also, if we sub this out, we get x minus x squared, move the x squared over, gives us x squared equals x, which does hold for a value of x of 1 or 0, which actually in a way proved idempotence, which is super cool. Good job, George. Now, if you've taken the course Math 1 CO3, you'll recognize this textbook, Mathematical Thinking, Algebra, and Number Systems. And one of the reasons I kind of wanted this topic is because we did look into Boolean algebra and how George Boole set up words with a logical number sets. So in my textbook, in the beginning, it describes a scenario where Ottawa is the capital of Canada and New York is the capital of the United States. Now, in this instance, I'd like to look at truth tables and how these propositions can be shown logically with numbers as a way of showing what's happening. So if we look at Ottawa being the capital of Canada as P, and New York as the capital of the US as Q, and then introduce connectives and or, we can assess how these propositions are affected by one another. So if we want to look at P and Q and P and Q and then P and Q and P or Q, we're going to start by looking at all the possible combinations of P and Q. So now that we've filled in the chart, I'd like to explain how the words would apply to this table. So in this situation, we have that if something is true and true, it's true, and if it's true but false, then it's false, and if it's false and true, it's false that they're and then if both are false, it's still false. And then over here we have true, true, if either or it's true, true, false, one of them's true, so it's true, false, true, again, one's true, so it's true, and then when both are false, it's false. So how does that apply with our words? So applying it to the words, here what we're saying is that Ottawa is the capital of Canada, New York is the capital of the US, so both Ottawa and New York are the capitals. And similarly, when one is not the capital, the addition or anding of both is then false for these situations. So in order for two things to be true, individually if they're true, together they are also true. And then if we look at the or case, we would note that only one of the two has to be true. But if both are true, one of them is true, so it's true. If one of them is true, if one of them is true, it's true. But then when both of the statements are false, one of the statements was not true, and so our output, again, is false. So this just shows a way in which the situation with Ottawa and New York can be put into a truth table involving true and false values. And from there, we can also say that true equals 1 and false equals 0. So then came along Cloud Shannon, who actually applied Boolean algebra to an electrical circuit for a way to test on paper and just through logical reasoning what the output in a circuit could be based on how it was wired, whether it be parallel, series, or a combination of the two. So if we remember from George Boole, x plus y denoted the or connective, and x dot y was the and connective. Now I actually messed up these drawings a little, so this parallel picture is a way of describing the or, and the ones in series is the and situation. So in the or one, you can tell if this gate was closed, no matter what this x is, the power is going to get through. So it just really relies one or the other to be open, and if they're both open, the power would still go through, meaning it would be true, which follows the table of values we just created. Now if we look at the and instance, you can notice if there's power over here, and it's trying to go along this line, it's going to need x and y to both be true in order to get to the output. So here is just a way that the Boolean algebra was innovatively used by Cloud Shannon to describe a way to test electrical circuits on paper. And I don't know if you guys have ever soldered or dealt with wires. It can be time consuming, use lots of stuff. So if you can test it out on paper and then go to make a circuit board, you've got better chances and you use less time, as opposed to just changing the wires 1,000 times and just guessing until it worked. Over on this side, I just have the logic gates drawn for the sequences. So in computer engineering or computer science, instead of writing out all this, for the and situation, so in series, if a chip was wired in series, on paper you could write it as this little semicircle with a straight edge, and then for the parallel or the or situation, it would be the same semicircle but more of a crescent with a curved edge. So I remember in high school we actually looked at these shapes in a math class, and it's super cool to see that the same reasoning we were taught then is still being reinforced in university. Okay, now I'd like to do a quick exercise combining a parallel circuitry and a series circuitry all in once using 3 variables, x, y, and z, and comparing the inputs of each of those and then their effect on the outputs. So I'm going to start by drawing it out for you. We're going to have an input, and then it'll be overall a parallel circuit with my z, and then my x and my y are going to be connected in series with one another. And then we've got the output over there. So you'll notice, if you remember, that the series is represented by an and. So x and y, and then the or was a plus sign, so or z, which is equal to x and y or z. Then I'm going to get going on the truth table. So we've got x, my y, and then what I'm going to actually do as a little shortcut is my x and my y as its own column. X and y, and then my z over here with my output. And there we are. if we were just looking at x and y, there's 4 possibilities. So true, 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 false, false, true, false, false. But then because we're adding in the third component, and for every component of z there's another 2, we're going to have 8 total possibilities. So just give me a moment to fill those out. So remember what I just said, there's true, true, but because of the z, we're going to add on a true and then a false. So a true and a true, just so we count for all those. Then we have a true and a false, a true and a false, which yields a true and a false. Then we over here have our false with our true, a false with a true, which gives with a true and a false. And then we've got the double falses, false, false, which comes again with its own true and false. So then, I'm going to go through and remember that in an AND gate, the only way there's going to be power at the end is if both of those switches are on, or both of those switches are closed. So looking at the diagram, the only way that the power is going to get to here, from over here through here, is if this wire is connected and this wire is connected, because you can't have power through the blank space. So instantly I'm going to go down through this and notice the only situations where this value is true is where these ones are true. So true, true, and then every other one of these is false. So false, 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 false. So just based on this, you might be thinking, how is there going to get to be power? But the key thing to remember is the Z was wired parallel, which means that any instance where the Z is true or the Z is closed, we will get energy to the output, because it'll always have this pathway of flow, no matter what's happening up here. So based on that logic, we can go through for the Z's, and anywhere a Z is true, our output is true as well. So for this one we have true, 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 true. So there we go, 4 outputs of true, or power, or 1, whatever you want to call it. So then what we're going to have to do is look at the OR. So the OR exists between X and Y, or Z. So if we just remember, write a little OR there, and then I'm going to notice that between a true and a false, one of those is true, which means our output's true. And then we've got a double false, which means that this is open and that's open somewhere. So false. Then we've got, oh, I got a little wonky there. So it's a double false again, which is going to yield a false for the same reason. And then a third double false, which will yield a false. Gotcha. Yeah. Right. 1, 2, 3, 4, 5, 6, 7, 8. Sweet. Yeah, so then in the end you'll notice that we started with the 4 situations, and then because right off the bat through the AND gate our possibilities were narrowed down, we then have the 1 extra true from that situation when the top was good, but this one was false. So therefore, we can see that in any instance where the Z was true, our output was true, and the X and the Y did in fact require both to be closed. And the instance where both were closed, but then the Z was false, did yield a true in the end. So there you are. I hope this exercise can help you out a bit with the assignment. Good luck!
And that's all, folks.